Hi everyone, we're Group 14 and we're here today to present Scout, a smart cargo operating unit with tethering. So what problem are we solving? Manual material handling is one of the leading causes of workplace injuries in warehouse environments. Scout addresses this by acting as a self-navigating car that autonomously follows a designated operator. And the system features optical detection, indoor location tracking, load sensing speed control, an LCD interface, and a full power distribution system. So for our engineering specs, we're using ultra-wideband or UWB as our indoor localization method. UWB gives us relative positioning at roughly plus or minus 10 centimeters. And moving on to our motors, the speed is capped at 1.5 meters per second, and it scales dynamically based on payload weight using our load cell system, and the weight measured by our load cell is also displayed on an LCD. And these will be the three engineering specifications that will be highlighted today during our demonstration. And before we get into our demo, on the component side, the UWB modules have been calibrated to achieve that 10 centimeter accuracy. Our battery pack runs at 24 volts with a 10 amp hour capacity, and is paired with a battery management system that handles overcharge, over-discharge, and short circuit protection. The motor drive subsystem is rated for 24 volts DC with a peak current of 40 amps. So now we will move on to our demo. So as you can see here, we have two ultra-wideband or UWB modules, one as a tag and one as the anchor. The anchor is the receiver and the tag is the transmitter or the initiator. And as you can see, they are at a distance of about 100 centimeters or about 1 meter. And as you see on the serial monitor connected to the tag, the real-time ranging measurements using double-sided two-way ranging. And if I move the tag about 50 centimeters away from the anchor, you can see in the serial monitor the change in distance. Our final model will utilize 3 anchors mounted on the cart and 1 module on the user, which will be the tag, and the anchors will be ranging the distance from the tag utilizing trilateration math and double-sided two-way ranging. So as you can see, the tag and anchor are at a distance of about 40 centimeters or 0.4 meters away from each other. And on the serial monitor, the output displays 0.4 meters with some deviance. And now the tag and anchor will be at a distance of about 150 centimeters apart or 1.5 meters. And on the serial monitor, the output is about 10 to 20 centimeters off from the actual distance measured, which is pretty close to our engineering specifications. So shown here is our custom UWB module with an ESP32 and a DW3000 module configured as an anchor. And on the serial monitor, you can see the double-sided two-way ranging is SPI initialized. The UWB initialization is a success and is configured as an anchor. So as a responder, it is waiting for a pulse signal from the tag as the initiator. Thus, the serial monitor has stopped printing, and there will be 3 anchors mounted on our cart and 1 tag on the user. Now the module is configured as the tag, as we can see in the serial monitor, and as the initiator, the tag is sending a pulse signal waiting for an acknowledgement from the anchor. And since there isn't an anchor present, the tag will continuously pull until it detects an anchor. Here's a summary of our UWB ranging accuracy across 10 test distances. The green rows meet our plus or minus 10 centimeter engineering specification. Those are the short ranges from about 0.3 to 0.8 meters. The yellow rows are borderline, just slightly outside the threshold, and the red rows show where accuracy degrades significantly, particularly beyond 1.2 meters. Overall, about 60% of our measurements meet the specification, more importantly at distances under 1 meter, which is exactly where our minimum following distance operates. The system performs well and consistently. The degradation at longer ranges is something we're actively addressing, although the degradation may be due to the fact that only 1 anchor was utilized. Meanwhile, for our final demonstration, we plan to implement 3 anchors, which will implement multi-anchor trilateration, which should bring back accuracy back within the spec across the full operating range.
This demonstration showcases the electrical subsystem that I designed for our senior design project. The purpose of this subsystem is to provide reliable power distribution while measuring the payload placed on the cart using a load cell. The system begins with a regulated 24-volt DC power supply. The bench power supply is being used to simulate the 24-volt battery that will eventually power the completed cart. This voltage serves as the primary power source for the entire electrical subsystem and is supplied directly to the custom regulator board. The first board in the system is the custom regulator PCB. Its purpose is to efficiently convert the 24-volt input into a stable 3.3-volt output using a switching buck converter. By using a buck converter, the circuit minimizes power loss while providing a reliable and consistent supply voltage. The regulated 3.3-volt output is then connected to the main custom PCB. This board serves as the central controller for the electrical subsystem. It contains the ESP32S3 microcontroller, which performs all system processing, along with the CP2102 USB to UART interface used for programming and debugging. The board also includes the programming buttons, power indicator LED, battery monitoring circuitry, and the connectors used to interface with the LCD screen, the HX711 board, and the remainder of the system, including our motor driver pins. This board acts as the communication hub between all of the electrical components. The load cell itself produces a very small analog voltage that cannot be measured accurately by the ESP32 alone. The HX711 is a 24-bit analog to digital converter specifically designed for load cell application. It amplifies the tiny signal from the load cell, converting it into a digital signal, which is then transmitted to the ESP32. The LCD connected to the main board displays the measured weight in real time, allowing the user to monitor the payload currently being carried by the cart and adjust speed accordingly. The second portion of this demonstration verifies the operation of the load cell measurement system. The first test uses lightweight objects weighing approximately half a pound. Once the object is placed onto the load cell, the aluminum beam experiences a small amount of strain. This strain is converted into electrical signal by the load cell, amplified and digitalized by the HX711, processed by the ESP32, and then displayed on the LCD. As you can see, the weight we're experiencing now is half a pound. The process is then repeated using a medium weight object, in this case about a 6.5 pound battery. Once again, the measured value updates in real time as the applied load changes. As you can see, the weight is around 0 with no weight applied, and as I apply the battery, it will go up to about 6.5 pounds in real time. Finally, the system is tested near its intended operating limit using about a 15-pound weight. This demonstrates that the load cell, HX711 interface, ESP32, and the LCD all function together to accurately measure and display increasing loads. As you can see, it's near 0 with no weight applied, and as I apply weight, it will go up to 15 pounds and be able to handle that load. This table summarizes the results obtained during the load cell validation testing. A variety of objects with different weights were placed on the load cell to evaluate the accuracy of the measurement system across its intended operating range. For each object, the measured weight was compared to its known reference weight to calculate the overall measurement accuracy. Most of the measurements achieved an accuracy between approximately 98 and 99%. The final row illustrates the system's performance near the maximum desired load of 15 pounds. Overall, these results demonstrate that the custom electrical subsystem is capable of accurately measuring payload within real time.
Good afternoon. My name is Davani Trent, and for this midterm demonstration, I'll be presenting the current progress of our motor control subsystem. In this demonstration, I'll be showing two key aspects of our motor control system. First, I'll demonstrate differential drive, where each of the two drive motors is controlled independently. By varying the speed and direction of each motor, the vehicle can move forward, turn smoothly, or rotate in place without requiring a steering mechanism. This differential drive approach gives the platform excellent maneuverability while keeping the mechanical design simple. The second demonstration focuses on smooth motor acceleration and deceleration. Rather than commanding the motors to immediately start or stop, the ESP32 gradually ramps the PWM duty cycle up and down. This produces a smooth increase and decrease in motor speed instead of sudden changes. This gradual ramping is important because it helps reduce the effects of back electromotive force or back EMF, which is generated whenever a DC motor rapidly changes speed. By reducing these voltage and current transients, we place less electrical stress on the motor driver, MOSFETs, and other power components while also reducing mechanical shock on the drivetrain. These demonstrations validate both the control algorithms developed for the project and the expected operating behavior of our final motor control system.
This is the serial monitor output from the ESP32 during the motor test. You can see the firmware boots, initializes the motors, then walks through each movement: forward, reverse, left turn, right turn, spin left, and spin right before completing the test. Each step is logged in real time so we can verify the sequence is running exactly as expected. This is our main firmware file. At the top, we pull in free RTOs for task management, ESP IDF for logging, and our motor module. The test sequence starts by initializing the motors, waiting 1 second after boot, then smoothly ramping both motors forward to 50% duty cycle. Once the forward run is done, it soft stops, pauses, then does the same thing in reverse. After forward and reverse, we demonstrate differential drive. For turns, we run one motor faster than the other, a 70-30 split, to stimulate how the cart would steer. Then, for the spin in place, we run one motor forward and the other in reverse at 40% each. Every movement uses a smooth ramp up and ramp down instead of cutting power immediately.
For today's demonstration, we were using the Citron MDDS30 motor driver instead of my custom motor driver PCB. During hardware testing of the custom board, I discovered that the MOSFET footprint had an incorrect pin orientation, causing the gate and drain connections to be reversed. Because the gate driver could no longer properly switch the MOSFET's battery voltage reached the gate driver but was never transferred to the motor outputs. Rather than attempting extensive rework on a high current PCB, I corrected the footprint in the PCB layout and submitted a revised version for manufacturing. Although the hardware is different, the MDDS30 behaves very similar to the custom motor driver. Both systems receive PWM and direction signals from the ESP32. Both use an H-bridge configuration to control the brushed DC motors, and both provide forward, reverse, braking, and variable speed control. This allows us to validate the motor control software and overall system behavior while the revised hardware is being manufactured. The main difference is that the MDDS30 is a fully integrated commercial motor driver, while my custom design uses TI DRV8701 gate drivers and together with external CSD19536 KTT MOSFETs. Designing the motor driver ourselves provides greater flexibility in component selection, current capability, thermal management, PCB layout optimization, and protection features such as current sensing and fault monitoring. Once the corrected PCB arrives, the same ESP32 control algorithms demonstrated today will be transferred directly to the custom hardware with minimal software changes.
This table summarizes the results from our motor demo. All 6 movement tests, forward, reverse, left turn, right turn, and both differential spins, passed at a 30% per second ramp rate. The 3 failures you see were from our initial settings where the ramp rate was too aggressive. Forward initially ramped at 150% per second, and both the regular stop and differential stop were running at 200% per second, which caused abrupt jerky movements. We tuned those down at 30% per second for acceleration and a slightly faster 50% per second for deceleration, and all tests passed after that. That wraps up our midterm demo for Scout. Today we walked through 4 key subsystems: UWB ranging, load cell sensing, LCD telemetry, and motor control. Each subsystem has been developed and tested independently, and the next phase is bringing them all together into one unified system. Once integrated, Scout will be able to sense its cargo weight, track a worker's positioning using UWB, and autonomously follow them at a safe and controlled speed. We're on track and looking forward to showing a fully integrated demo next time.